Hey everybody! Today we're diving deep into the world of operating systems, specifically process scheduling. Imagine your computer as a busy coffee shop. You've got baristas, which represent the CPU, customers lining up with orders, and a system for deciding who gets served first. That system, my friends, is process scheduling. Without a good process scheduler, things would get chaotic really quickly. Imagine a world where you start watching a YouTube video, but then your web browser freezes because another program hogs all the CPU resources. It makes sure that everything runs smoothly and efficiently, even when you've got tons of stuff going on in the background. Stay tuned! Okay, so we've established that process scheduling is like the unsung hero of your operating system, working tirelessly behind the scenes to keep things running smoothly. But why is it so crucial? Let's break it down. Firstly, efficient process scheduling ensures that all processes get a fair share of CPU time. Imagine a scenario where one program, maybe a resource-intensive video editor, hogs all the CPU power. This would leave other programs starving for resources, leading to sluggish performance and frustrated users. Secondly, it plays a vital role in maximizing CPU utilization. A good process scheduler ensures that the CPU is always working on something, minimizing idle time and maximizing throughput. Thirdly, process scheduling directly impacts system responsiveness. Without it, your computer would be a chaotic mess of unresponsive programs and frustrated users. Now let's get our hands dirty and delve into some of the most common process scheduling algorithms, starting with the simplest one, first come, first served, or FCFS. As the name suggests, this algorithm is all about fairness and order. Processes are treated like customers queuing up at your local coffee shop. The first one in line is the first one served. Simple, right? That's FCFS in a nutshell. Each process gets to use the CPU in the order they arrive, and they get to keep it until they're finished with their task. While this might seem like a fair system, it does have its drawbacks. Let's say a customer at the front of the line orders a super complicated drink that takes ages to prepare. Despite its simplicity, FCFS can sometimes be inefficient, especially in systems where processes have widely varying execution times. Section 4, Shortest Job Next, SJN, Scheduling. Alright, now that we've covered the basics of FCFS, let's move on to a slightly more sophisticated algorithm, Shortest Job Next, SJN. As you might have guessed from the name, SJN is all about efficiency. It prioritizes shorter processes, aiming to get them in and out of the CPU as quickly as possible. Think of it this way. Imagine you're at the supermarket checkout, and you have the option of choosing between a long line with customers who have full carts, or a shorter line with customers who only have a few items each. Which line would you choose? Most likely you'd opt for the shorter line because it means you'll get through checkout faster. That's precisely what SJN does. Despite its limitations, SJN is a valuable scheduling algorithm in scenarios where minimizing average waiting time is crucial. Section 5, Priority Scheduling. Moving on, let's talk about priority scheduling, an algorithm that adds a new layer of sophistication to the mix. In this scheme, each process is assigned a priority level, and the scheduler always selects the process with the highest priority to run next. Think of it like a hospital emergency room, where patients with more critical conditions are prioritized over those with less severe ailments. Priority scheduling can be a very effective way to ensure that important processes get the resources they need promptly. However, it also introduces the potential for starvation, just like with SJN. To mitigate this, many operating systems implement aging, which gradually increases the priority of processes that have been waiting for a long time. Section 6, Round Robin RR, Scheduling. Last but not least, let's explore Round Robin RR Scheduling, an algorithm designed for fairness and responsiveness in time-sharing systems. Imagine a merry-go-round where each child gets a fixed amount of time to ride before they have to get off, and let the next child have a turn. That's essentially how RR scheduling works. The scheduler assigns a small time slice, called a quantum, to each process. Processes take turns using the CPU for their allotted time slice. Once a process's quantum expires, it's moved to the back of the queue, and the next process in line gets its turn. This cycle continues, ensuring that all processes get their fair share of CPU time without any single process monopolizing the system. R scheduling is particularly well suited for interactive systems where responsiveness is crucial. So, the next time you're zipping through tasks on your computer without a hitch, remember to thank the unsung hero working tirelessly behind the scenes, the mighty process scheduler.